All right. So today, on top of this kind of introduction to the course, expectations, all that, I wanted to have the rest of this time be dedicated to kind of building up our fundamental understanding of a couple of things. We're going to look a little bit at some of the notation that I will be using for this course, but that's not really the focus. Really, the focus of what we're going to be covering here is going to be, what are numbers? We are here to do math, and I find often that I can get a student who can tell me that a solution set is all real numbers, and then have absolutely no idea what a real number is. And so what we are going to do today is show that not knowing what a real number is super fair, because it's really hard to define. We're going to work our way up to it. We're going to go through the different types of numbers. We're going to justify, why do we need the numbers that we currently have? Why did numbers get so complicated? I hear that a lot. I loved it when it was just counting on my fingers and all that. Really wonderful. Why did we have to start introducing letters into numbers? All that fun stuff that you hear so often levied against math. And we are going to start in the most probably obvious place to start, with kind of building up a framework for numbers. These are what we might sometimes refer to as the counting numbers. They are very literally numbers that you can count on your hand. And I don't just mean up through 10. I mean that you could conceivably just keep going one at a time, get all the way up through. We are going to call these our natural numbers. In your notes, you will see that there is a little symbol next to this. This is the way that I will refer to the set of all natural numbers. It's like this weird bold script N. In fact, that's going to be kind of true for all of these sets of numbers. We generally are going to have something along that style for them. And very simply, natural numbers are just our counting numbers. This is 1, 2, 3, so on, forever and ever and ever and ever. The natural numbers do a really good job at addition specifically. Actually, the natural numbers, if the only thing we could do with natural numbers was add them, the natural numbers would be a perfect place to stop. What do I mean by that? Well, I mean, if I take two natural numbers, randomly pick, in this case, 3 and 14, and I add them together, what kind of number am I always going to get 100% of the time? Always going to get a natural number every single time, as long as I am adding two natural numbers. So if addition was all we could do with numbers, we'd be perfectly happy to just be done at naturals. Okay. Obviously, though, addition is not going to be where we are stopping. We can do a little bit more with numbers than addition. Kind of that next step up from addition. First, we learn about counting numbers, then we learn how to add them. What is kind of that next step? And are the natural numbers a good place to try that? After addition, we learn subtraction. And are the natural numbers enough to do all the subtraction that we want to do? No. Now, this idea of enough, this idea that if I combine two elements with a particular operation where I land in the same set where I started, we call that closure. So the fact that adding two natural numbers will always give me a natural number, we would say something along the lines of that the set N is closed under this particular operation, in this case, addition. Which is basically just a way of saying we can combine these elements in any way, and we're not like creating new numbers as we go. We don't need to add any new numbers to what we are working with in order to be perfectly happy. Okay. Subtraction introduces a problem. Why does subtraction introduce a problem? What kinds of numbers do we run into that aren't accounted for by just what we can count on our fingers? Negatives. Give me an example where I would run into an issue, where I would not have closure with this subtraction. Any old example. 3 minus 14, fantastic. Exactly what we have here. Now notice that 14 minus 3 does still give us a natural number. And that's cool, but all we need is one example where it doesn't work. For instance, 3 minus 14, where we get a negative number, and all of a sudden we see the natural numbers aren't enough. If we want a number system that can handle addition and subtraction without having to bring in foreign elements, then clearly the naturals aren't a good place to stop. Okay. So what kind of numbers do we need to add in here in order to account for what subtraction is tossing at us? What kinds of numbers are we missing that we really need in order to do subtraction properly? Not yet. Put an asterisk in there. We'll get there. Negatives. We need negative numbers in order to properly be able to do 3 minus 4. That's what we're missing. We're missing negatives. One other number that is not really positive, it's not really negative. We definitely need it for subtraction, though. What number are we also missing? 0. We're also missing 0. Okay, so we need the negatives, and also we need 0. So that's kind of the next step. If we wanted to think about our numbers here, we start with the naturals. We've got like the bubble that is all the naturals. This is like 1, this is like 7, this is like 1,000. Right? We need to expand that bubble to include positives and negatives, and also 0. It's like 0, -7, so on. This particular set is called the set of integers, denoted very predictably by a bold script Z. I think like the German word for integer starts with a Z, and so we get a Z here. And these are going to be our positive or negative, what I am going to refer to as whole numbers. This is not referring to whole numbers as in like the set of all whole numbers. This is referring to whole numbers as in not fractions. These are positives and negatives and not fractions, and also what? And 0. Also needs 0. And what we find is that the integers are a pretty good place if we want to do addition and subtraction. In fact, we might say that Z is closed under addition and subtraction. And that would be true. We can add and subtract integers as much as we want, and we don't need more numbers to do that. All right, so we're getting closer. We're happy with subtraction. We're happy with addition. Notice that we didn't lose the natural numbers when we expanded our definition of what it means to be a number. The positives are still in there. Now there's just a little bit of extra stuff. Specifically now the negatives and 0 are also. So 1 is a natural number, but also it is an integer. It is both. All right. What other operation can we do with these where we're totally happy? So we can add them, we can subtract them. What else can we do? We can also multiply them, right? If we multiply two whole numbers, two non-fractions, then we are also completely fine. It's also closed under multiplication. Okay, not super relevant, but it does give us the need for what is next, which is what breaks our integers. What operation can we do that starts making us need more numbers, in particular, the fractions that we were talking about? Division. Okay, so we need to be able to account for division. Just like before, we can divide integers and get an integer. That is entirely fine. That is possible. But it's also possible to not get an integer, particularly if I flip this, I get something that I have not properly defined as a number. We know what we want that to be. We want this to be some kind of fraction. We are going to again need to expand this bubble. Positives and negatives are lovely if we're doing addition and subtraction, but we need to make it a little bit bigger here to include fractions. So this is z, and this is going to be q. We'll talk about that here in a second. That's like 1/2, -5/4, so on. I want to be a little bit particular, though, when we say the word fraction. I can come up with fractions that aren't integers, or that aren't, in this case, rational numbers. So what we would describe this as is the set of rational numbers, denoted by Q. Makes a little bit more sense, quotient for the rational numbers, and that is like all of our plus or minus fractions. So positive fractions, negative fractions, whatever we like. Before making a more robust look at this, though, again, I want to be very specific when I am talking about fractions. I very deliberately mean a fraction where we have an integer on top and an integer below. If you have worked with trig at maybe a higher level than geometry, then you will have seen fractions that look like this. And that is a fraction. Definitely is a fraction. You've got a numerator, you've got a denominator. It is not a rational number because pi is not a whole number. All right. So we have this need to be able to be written as integer over integer. Maybe the way we say that is that all of our rational numbers can be written as m over n, where what must be true about m and n? What kind of numbers do m and n need to be? They need to be integers. So the way we might write that is we might say that m and n exist in the integers. Again, don't get scared. I know it looks horrifying. This is just saying that what we want is fractions. Specifically, we want fractions where the top and the bottom are just whole numbers. That's all that's saying. This little e here means that these two numbers live in the set of all integers. They are integers. Okay, so I gave you an example, in this case pi over 3, that I said was not rational, but actually it's a fairly fair question to ask and say we're good for addition and subtraction. We're good for multiplication and division, and by good I mean we're closed, right? So Q is closed under all four of these kind of operators, completely closed under each of those. And so is this a good place to stop? Is this all the numbers have for us? Obviously, we know that the answer is no, but that getting to that answer is a lot less trivial than it appears. Because actually, this was a problem that really, really plagued a lot of the early kind of mathematicians who were dealing with this. Some very big names were wrong and said that, in fact, every single number that we can come up with can be written as integer over integer. Every single one. Among them, and we'll talk about this more here in a second, actually, really where we started to see the cracks in this assertion, the idea that we are done once we hit Q, is when we look to geometry. There are a couple of very, very basic shapes that when we consider them, make this feel a little bit iffy. They draw up some question marks, and maybe it's still true, and we're just not good enough at measuring things to be able to categorically say that whether or not this is the case, as we're going to see that that is not the case. So a very basic problem that came up is if we look at a right triangle where both of the legs are of size 1. Now, what is the formula that I could use? What is the theorem that would allow me to figure out the length of that hypotenuse? What could I say? What would we say? Pythagorean theorem. So Pythagoras came up with this particular formula. And what is that? Absolutely. Or otherwise written, a squared plus b squared is equal to c squared. Fantastic. In this case, a and b are both 1. 1 squared is just 1. So this is like 1 plus 1 is equal to c squared. And with a little bit of finagling and some hand waving, we'll say that c is equal to the square root of 2. Very simple triangle and a very obnoxious number that comes from it. Square root of 2. Okay. This was one of several examples that really gave people a headache. There's a story about Pythagoras teaching on a boat, and he makes the big claim that every single number is rational, every number can be written as a fraction, and one of his students raises their hands and says, but Pythagoras, what about the square root of 2? And Pythagoras, as an answer, throws his student overboard. A level-headed, reasonable teacher response. And it's fair. A lot of speculation was that, hey, it exists, and we just can't really figure out what it is. We just don't have the precision to be able to tell. And it turns out actually not to be the case. And there are other numbers in here that show up in geometry. Pi is one that comes up a lot that you guys have definitely seen before. You might have seen E as well, being a number that shows up all over the place. And these numbers were problematic. E not so much. E got discovered later. It's called Euler's constant. So Euler discovered it back when he was doing math and being alive. But all of these other numbers still created. So we're very happy with the rational numbers, but we're less happy that there appears to be a bunch of numbers that still exist that don't quite fit the mold of what it is to be a rational. Okay, so we need to expand our definition of a number because it turns out that in fact these are not rational numbers. There is no fraction that we can create that properly works. So we need to expand our definition of numbers, and the way we're going to do that is incredibly unsatisfying. We're going to say we want our new definition of numbers to be all the ones that are nice and rational, and all the other random stuff in between. And that's just what a number is going to be. So we expand our bubble, and this is where we are almost done. These are the real numbers. So whenever you say all real numbers, you are referring to every rational number and also all of the middle, in between random bits that fit there. And there isn't a good way to categorize them. A lot of them are roots, some of them aren't, some of them get really nasty, some of them are variations of pi and e and whatnot, and there's just not a good way to deal with it. And so we thought. Okay, this is a fantastic place to stop, which we are not going to do. We're going to go out one bubble further. We then later realized the real numbers are fantastic. They are really, really good. There's a little bit more to the story that is a little bit easier to kind of classify, and that is with what we call the complex numbers. This is C. And the way we define a complex number is it's a number that has some kind of real bit combined with some kind of imaginary bit. Right? Imaginary bit meaning it'll have the number I in there, which we'll talk about more in like a few weeks. Right? But these are like 2 plus 3i. Anything that has I in it is a complex number, but it's also important to note that all of the other stuff that we've looked at is also a complex number. Complex numbers now just also allow for I to exist. Specifically, the way we might define this in that kind of math speak like we did with rationals is we might say a number is a complex number if it can be written as a plus bi, where a and b are just some kind of real. Notice if you set b equal to 0, which is fine, 0 is a real number, then you get all of the real numbers. So this definition works for all the new stuff that has i's. It also works for all the old stuff as well. So everything is a complex number. Sometimes we don't want to allow complex numbers into our solutions, though, so oftentimes we stop at roots. But these do exist. If we were to kind of make a comparison like what we have been doing, this kind of search for closure with addition and subtraction, multiplication and division, complex numbers solve the issue of roots. Specifically, they solve the issue of taking roots of negative numbers, which now we can do again. So, still there. And for now, this is good. When we talk about vectors, we'll see that this can be kind of rearranged ever so slightly, but for now, it's good. All right, questions here? Since we have some time, let's take a look at a couple of the examples. So looking here at these practice problems, in this case, we are being asked to figure out the classifications for the given number. And it also says here, be sure to include all relevant classifications. Okay, so it might be easy to identify like the outer shell that it lives in. I think a lot of students struggle with then figuring out, okay, which direction do I go? If it's like the square versus rectangle question. If it's a square, is it also a rectangle? If it's a rectangle, is it also a square? Kind of thing. So let's work through that. Let's see if we can figure out what is going on here. So looking at A, we are given the number 1 and 3/4. So let's just kind of work our way from the innermost outwards and see if we can't figure out what's going on. So 1 and 3/4, is this a positive whole number? No, it's got that fraction in it, definitely not a whole number. This is not a natural number. Is this a positive or negative whole number? It's still not a whole number. Okay, not an integer either. Is this a positive or negative fraction, or can it be written as a positive or negative fraction? Absolutely. How could I maybe rewrite this to make it really clear that this is integer over integer? What is the kind of complex fraction form of this? 7/4 is fantastic. So notice that 1 and 3/4 mixed numbers are garbage. I'm showing this as an example. I will generally not use mixed numbers if I can avoid it. Writing this as 7/4 makes it very clear that this is an m over n case, which means that this does definitely live in Q. Okay. If you were to write Q, you are mostly correct. That's fantastic. Q is I would say the tricky one to identify. It's like the relevant one to identify. But then there is also the question of, if it is rational, is it also real? And the answer is yes. The real numbers are everything that can be written as a fraction, and also all the other stuff. This can be written as a fraction. This falls under that definition. Right? So it is part of Q. It is also part of R, part of the real numbers. Okay? And then, is this either a real number or a complex number? Absolutely. This is also part of C. In particular, if we're thinking about like this A plus BI form, B is 0 and A is 7/4. So it is a rational number, but on top of that, it is also a real number. It is also a complex number. The TLDR here is you're always going to say yes to complex number. If I ask the question, is it a complex number? The answer is just yes. And then you're kind of working your way on. But I think this kind of way of eliminating from the inside is a little bit helpful. And then as soon as you find one that works, the rest all work. Okay, let's take a look at C here. This is pi plus 7i. Is this a positive whole number? Definitely not. So not natural. Is this a positive or negative whole number? Definitely not. Still not a whole number. Can this be written as a fraction? Give you a hint. If it has pi in it, if it has a square root that hasn't been simplified in it, the answer is just no. Right, so pi, square roots, those kind of things, those are all going to fall under that umbrella of can't write them as fractions. In this case, pi plus anything, not going to be able to be written as a fraction. So definitely no. Does this have an I in it? For C? C does, which means it's not real. If it has an I, it means it's not real. This is just going to be part of the complex. But if we look at B, does B have an I in it? No. So it's definitely real. And if it's real, then it also is complex. Okay. What about 0? Is 0 a positive counting number? No. Is 0 a positive or negative counting number or 0? Definitely. This is Z. Oh. And if it's Z, what else is it? Q, R, and C. All. Okay, what's mean about E? I threw in an X. Okay, so what is this classification going to depend on? It's going to depend on whatever X is, right? If X is a natural number, then 7x plus 4 is definitely a natural number. If X is an integer, then 7x plus 4 is definitely an integer. If it's rational, then this is going to be rational. So on. You could just say for this one, it depends. Whatever X is, that's going to be characterized. But it is definitely 100%. All right, how are we feeling about classifications of numbers? Any questions so far? Feeling good? Not too bad? Okay. And again, I will write like this. I will explain what it means as I write. Like I'm not just going to put it up there and then leave it for you to decipher. I will tell you what each of the symbols is as I'm doing. Okay, that is what I wanted to cover as far as stuff that you could possibly be assessing. Questions from 0, 0 are going to look like this. Maybe like some true false about like if it is a real number, then it is definitely rational. Things like that. Those can be a little bit tricky, but for the most part, this is very much within what I'm going to kind of assess. So we are going to take a slight diversion. I want to preface this with it is very fair to be about to be confused. Because what I'm going to talk about does not make sense. This is purely me spinning my math wheels. This is the byproduct of studying math at college for 4 years. But it's some pretty cool stuff. I think, anyway. And that is a question, again, that we don't need the answer to for this class. That is a very difficult question to just kind of approach. If you would like deeper explanations, or if you would like to see the justification behind why these things that I'm saying are true, I have office hours every Tuesday. I will be here from 2:45 to 3:45. You are more than welcome to come find me. If that time does not work and there's another time that does, and you need help on a classwork or have a question from class or whatever, just let me know and I will figure out a time that will work for you. So if you are kind of more interested, yes. Wednesday, so we're leaving Wednesdays fairly open for seminar. So like Wednesdays during seminar would also be a fantastic time. Just make sure you tell your teacher. Yeah, so all of those, fantastic. My math round. And that is that in the 1930s, a new question about these numbers kind of arose. And we can kind of start to pick away at that with a very simple question, which is how big are each of these things? Fairly easy to answer. If we think about the natural numbers, if we think about just the numbers that we can count on our fingers, how long are we able to count until we run out of numbers? Do we ever hit a maximum? No, okay, we can keep counting up and up and up, on and on and on forever and ever and ever, and never run out of numbers to hit. Fantastic. We would describe the size of that set. We would say it has an infinite number of elements. Very cool. But the integers also have an infinite number of elements, and the rational numbers also have an infinite number of elements, and the real numbers also, and the complex numbers also must. And the question is, are there differences between those infinities? Are there sets from the ones that we've looked at today that are bigger than the others? Does it follow the logical order that you expect? And kind of what does it mean to have an infinity that is bigger than another? Okay, so we are making this comparison. We'll start with just comparing the natural numbers and the integers. So in one hand, in one bubble, we have all of the positive whole numbers. In the other bubble, we have all the positive whole numbers, we have all the negative whole numbers, and we have 0. How would we expect these to compare? Which one should be bigger? You'd expect adding all the negatives to make it bigger. In fact, you might say, if we think about, we're going to use, I mean, not in this class, but generally we would say this refers to like the size of set n. We would expect that n should be like, essentially that our set should be like double and one more. Right? If 1 is in the natural numbers, then 1 and -1 are in the integers. If 7 is a natural number, then 7 and -7 are integers. And also 0 is there. So we would expect like double and then a little bit of extra. Like 2 times and then plus 1. And it turns out that that is not what you get. That in fact they are the same size. Super weird. How is it that we can take a set and all we're doing to that set is throwing a bunch of stuff into it? How is it that we can do that and not have it change the sign? Short answer is infinity is weird. Very, very weird and very, very funny. Again, obviously, I have a more satisfying answer to that. But yeah, it turns out that the number of positive numbers is the same as the number of positive and negative numbers. Because infinity is weird. How does that compare then to the fractions? Surely there are a lot of fractions, right? Because we can combine like any kind of integer over integer. There are so many ways that we could do that. Surely there are more fractions than there are numbers that we can count on our hand. And the answer is, again, they're the same number. There are the same number of fractions as there are just numbers that you can count on your fingers. Whenever you run into that, whenever you have a set that can be matched with our natural numbers, we say that that set is countably infinite, or that the size of that set is countably infinite. Because it can be matched to the counting numbers, right? Natural numbers, counting numbers. Okay. So we have our kind of useful numbers. We're mostly going to be working with rational numbers. Some reals towards the end, but mostly working with rational numbers. Those are like the bulk of what we know. That's the bulk of what we use. And then we said, okay, well, there's some like weird bits in the middle, like just some random little things like square roots and pi and e and all sorts of just random stuff that kind of fills out, and then we get the real numbers. That's all we did, right? We took the useful ones and then we filled it in with all the weird ones. That's great. How much did we fill in? How much of our number line did we just kind of fill in there? Is it the same size? Is it a different size? And Cantor ended up showing that it is a different size. That this is actually one of the first instances in which you see an infinity that is bigger than what we were working with. 1, 2, 3, 4 size. And it is so big that if you were to just think about all of the numbers between 0 and 1, infinite number of fractions that you can come up with between 0 and 1. Right? Infinite number. And you were to randomly select one of those numbers. Just randomly pull one and check, is it a fraction or is it not a fraction? There are so many of these filler numbers. There's so much of just this random stuff, like roots and just weird pies and all of that, that your odds of picking a fraction are mathematically, literally, 0. There's a 0% chance from the infinite number of fractions that you could pull that you would be able to pull a fraction. It's just kind of weird. It's like we have this number line, and we did a really good job of defining the stuff that was in the number line, and then it turns out that most of that isn't even what we're using. Most of the number line is just random filling. So it's not random filling. A little bit more, and if you want to look at it a lot more, become a math major and take a real analysis class, and then you too can rant about sizes of infinity in front of a bunch of children. And if that's not what life is about, then what even is? All right, that is all I've got for you. We've got about 3 minutes left. I know that there are a lot of people walking back and forth. For my sanity, and just so that, you know, don't enjoy having people slip out, wait until 2:30 before you go. Since we're done, you're free to pack up and all that, but just wait until 2:30. I will tell you guys when to go. As far as getting to like the bus circle and all that, you were hopefully told this in seminar, maybe not. You are no longer able to use the downstairs math exit or the downstairs English exit to get to the bus. So now what you are going to want to do, construction and safety precautions and all that. Now what you are going to want to do, you can still exit by the guidance counselor's office. You can still exit by the science exit. You can still go by the 100s. But I would say either use the 300s or 500s if you need to get to those. So fastest way is probably down the main stairs and then out by the guidance counselor. All right. Shruti, we're just about done if you want to, like we've got like 15 more seconds. Yeah. Yeah, absolutely. There you go. All right.